For 7?
Yep.
Is that right? Okay. So it's asking us here to write the equation for the exponential function. So I'm given 2 data points for h, 2 xy's. So we'll have, we know we're going to write something, h of x equals a times b to the x. So if I plug in the first data point, I have 3/4 equals a times b to the -4. If I plug in the second data point, I have 3/2 equals a times b to the -2. I'm going to think about these as equations a and b. To solve this system, I'm going to take equation b and divide it by equation a. I always pick the one with the bigger exponent as the top. So that means I have 3/2 over 3/4 equals a times b to the -2 over a times b to the -4. So far, so good. Yeah, it just the negative got like merged into the top of the b there, I think. So far, so good. 3/2 divided by 3/4 is 2. Right, 1.5 divided by 0.75 is 2. You could do that on your calculator if you needed to. Not a big deal. The a's reduce, and then I subtract exponents. So -2 minus a -4 is +2. And so I get that b is the square root of 2. Now, why don't I need the plus or minus? B's are never negative. Good. So now that I have this, I'm going to take one of the 2 equations. I'm going to use equation b. And I'm going to plug that in for my new answer for b and for b and solve for a. What do I get when I do the square root of 2 to the -2? Well, what's the square root of 2 squared? I get 2. And then I need to, then I have it to the -2 to the -1. That is 1/2. Again, you could type that into your calculator if you needed to, not a big deal.
Why is it still 2 to the negative?
So I thought about this as, remember, exponent of an exponent, they multiply. So -2 is like 2 times -1. So I thought about it that way. So I get that a is 3. So if I put the 2 together, y equals 3 times square root of 2 to the x. Let me show you something else you can do with your calculator for this kind of a problem. You remember way back in like chapter 12 where we did like the models? We did like power reg and lin reg and all that stuff. This process that we did here was basically just an exponential reg, like an exponential regression. So if I do that, if I enter in some data points, so remember for the problem, the x was -4 and then -2. And the y was 3/4 and 3/2. And I exit out of here, and I do stat, calc, and I'm going to find exp reg using L1 and L2. I'm not going to bother storing this because I don't have to do anything with it when I'm done, right? It just wants the equation. Hit calculate. So it tells me the A is 3. The B is 1.4142, yada, yada, yada. Guess what that number is? It's the square root of 2.
So when you divide the two
Equations?
how can you do B divided by A?
So I usually want to use the bigger exponent in top, so that the reason I do that is so I don't have a negative exponent to solve for later. And that's just like a hassle, right? Like I can avoid having to deal with that hassle by choosing to put the bigger one or the bigger one on top, or the bigger one on top, and then I never have to deal with that, which just feels like a good deal to me.
So I did A divided by B, I got I did 3/4 divided by 3/2.
Yeah.
1/2.
And you get 1/2, and then A times, or you get B to the -2. And it's like, what do I do with that? Yeah. You can avoid that just by making sure you put the bigger exponent on top. Yep. Okay. Anybody else? Again, that trick I just showed you, doing like using the exponential regression to do that. Helpful, right? Even if it's just as a check, like that's a nice check to basically have it spit out the answer for you, right? Okay. Last call on questions. Anybody else? If you haven't started this, you may want to get on that, because this is a big homework set. Did you look how many problems are in this homework set? Let's just give everybody a nice little reality check here. 7 pages, it said. We're going to do all of it. A little while. But don't dig yourself a hole, because there's going to be a lot of stuff to do here, right? So like, I know that we like to wait till the weekend. Maybe try to do some stuff during the course of the week, so you don't have like, oh my God, it's like a never-ending like just avalanche of math problems for me to take care of. Like, try to get some done in the meantimes. Now, if you're a senior, remember all your problem sets are done, right?
Yeah.
What should you be working on right now?
Review packet.
Review packet. When is that due? May 1st. Right? Your last day? That's your last day, isn't it?
Yep.
Yeah, I need it in my hand by the end of school on May 1st. Okay?
Okay.
Do a good job.
I'll do a great job. It'll help you.
It'll definitely help you.
Perfect.
All right. Seniors, today is the last stuff that you guys will be responsible for, as far as like material that might appear on your final. So let's start. Today we're going to be talking about logarithmic functions. So our definition of a logarithm basically just states that given b and x greater than 0, with b not equal to 1, the exponential equation b to the y equals x is equivalent to the logarithmic equation log base b is equal to y. So what is this logarithm telling you? What is log base b of x really telling us? It doesn't tell us that x is equal to y. It's the exponent that I need to raise b to in order to get x, right? So if I plug this in, right, where I've just plugged y in, or log base b of x in for y, to the first equation. You guys see what I did there? Look what happens. Log base b will cancel with exponent base b. So you get x. What would happen if I did the reverse, where I took this x and I plugged in b to the y? It appears the same thing is happening, that log base b will cancel with the exponent base b. This idea of logs canceling exponent bases is the key idea for chapter 15. This is it. This is the fundamental idea that we'll be using all over the place from here on out, is that I can use a logarithm to cancel out an exponential, and I can use an exponential to cancel out a logarithm. This is it. That is the big idea, and we'll be building off of that from here on out, but that is the core idea, which again, the hope is that we remember a little bit of that from Algebra 2 that wasn't that long ago. All right. The example here says evaluate the following logarithmic expressions. Now, I acknowledge that you could just type this stuff into your calculator, right? If I want to type in log base 4 of 16 into my calculator, I press the math button. I scroll all the way to the bottom and grab the command called log base. That allows me to put the little subscript 4 in there. I type in the 16 and boom, answer comes out. What if we want to do this without a calculator though? Because that's going to be a nice building block for making sure we understand like this relationship between logs and exponentials. So if I have log base 4 of 16 and I want to evaluate this without using my calculator, what I want to do is I'm going to translate that into an exponential equation. So I'm going to write this as log base 4 of 16 is equal to y. I'm going to use my definition now of a logarithm and say 4 to the y is equal to 16. Well, what's y have to be in this case? 2, right? 4 squared is 16. So we're done. The other way of thinking about this is, can I write 16 as a base 4 number? 4 to what power gives me 16? That's 2. Log base 4 cancels with exponent base 4, and we're left with 2. That's kind of the way I like to think about it. I think that ends up building a little better intuition going forward, but either way, either approach is appropriate. So here we have log base 5 of the square root of 5 is equal to how do I rewrite square root of 5 as 5 to some power? Yes, the square root is the same as a 1/2 power. And then log base 5 cancels exponent base 5, and we're left with 1/2. Is that okay? So now we have log base 3 of 1 over 27. As soon as I see a fraction, I know I'm going to need a negative exponent, at least if my base is not a fraction. So I think of that as 27 to the negative 1. And now I just need to think of 27 as a base 3 number. 3 to what power gives me 27? 3 to the third. And if I have an exponent of an exponent, I can multiply those. And then log base 3 cancels the exponent base 3, and we're left with just negative 3. Log base 12 of 1. How do I rewrite 1 as a base 12 number? I know any non-zero number to the 0 is 1. So does that tell me log of any base of 1, what's that going to equal? 0, yeah. How about log base 8 of 8? Yeah. So I know that I can rewrite 8 as just 8 to the first. So log base 8 cancels exponent base 8, and we're left with 1. So our takeaway here is that log base b of 1 is equal to 0 for any base, and then log base b of b is equal to 1. So if the base is the same as the argument, the log is equal to 1. Regardless of the base, if the argument is 1, the log is 0. I guess we've done all that, but I'll drop that in. So again, here are the basic properties. We've talked about all of these already. So we wrote up the first two, and then those second two we showed right away here, right? So we'd kind of written that all out already. So some notation for us. There's two special logarithms that get used all the time, so much so that they have special names and special symbols. So the first one is called the common logarithm. The common logarithm means that the base is 10, but when we write log base 10, we never put the 10 there. We just write log, and we put no base, and everyone understands that the base there is 10, but because we use it so often, we don't bother to write the base there. Just like when you write a square root, you don't write the 2 inside the check mark where the index would go, like we would for a cube root, because everybody knows a square root is just index 2. We don't write it because we understand that to be the case. The other special logarithm is called the natural logarithm. That one is log base e, but again, we never write log base e, we just write ln, and everybody that reads that understands that, oh, hey, that's just the common logarithm, that's log base e. We use it so often, we've created a shortcut where we don't want to write all the notation. Okay. So let's just, do a little practice using these guys. So log base 1,000. Well, what is the base if I don't write anything when I just write log? 10. So I need to rewrite 1,000 as 10 to some power. I know 1,000 is 10 to the third, right? 10 times 10 is 100, times 10 more is 1,000. Log base 10 cancels with exponent base 10, and we get 3. Does everybody feel okay here? Part B, we have log of the 5th root of 10. Ooh, how do I write the 5th root of 10 as an exponent? The 5th root is the same as what power? The 5th root is the same as 1 power. 1/5. Yeah. So log base 10 cancels with exponent base 10. We're left with 1/5. About log of 0.01. So when I look at this, I recognize, oh, hey, 0.01 is 1 out of 100. It's like 1%. And that I recognize is 10 to the negative 2. And log base 2 cancels exponent base 2, and we're left with negative 2. Well, the way I looked at it is 100 is 10 squared. And because it's a fraction, it's negative. Right? So I just used that same idea when we had the 1 over 27. But this was easier because 100 is like, that's 10 squared. Like that's one you should be able to look at and go, got that one. And then it's just negative because it's a fraction. If you didn't recognize 0.01 as 1 out of 100, if you do on your calculator 0.01 and you do the fraction command, it'll give it to you. And it's like, now I see what to do with that. So you could do that as well. The next one, we have D equals e to the natural log of 5. I guess I just write that. I know exponent base e cancels log base e. So that's just 5. I am using this property that log base exponent base b cancels log base b. Mm-hmm. Yeah, because we recognize the natural log is base e. So log is base 10. ln is base e. Yeah. Oh, yeah, just my messy penmanship, probably. Or I crossed it out so fast you didn't have a chance to look before it. My apologies. So we have the next one, 2 equals log of x. So I can use my definition of a logarithm here, right, which would say 10 to the 2 is equal to x. So it's 100, right? And then ln y is equal to 5. Again, I'm going to use my definition of a logarithm. So I know e to the 5th is equal to y. And that's as good as we can do. You type e to the 5th in your calculator and get decimal if you wanted to, but let's just leave it as e to the 5th, right? Nobody wants some big chunky decimal. Pass, man, pass. Now, the natural logarithm and common logarithm are so frequently used that your calculator has a specialty button for each of these. Remember before, to show you how to type in log of a base, we pressed math and then went to the bottom and used the log base command. But your calculator has just the regular log button right here. If you need log base 10, it's right there. So you can just type in like, log and then the number. Or if you need the natural log, right below log is the ln button. So if you need the natural log of 12, you can just from the main screen and do that. Notice that those will give you the same answers if I did math, log base, and I filled in a 10, and then I did like 51.37. Right, still the same answer, but like one button versus like 12 button pushes. Like, give me the one button push, version. Like, I'll take that. Thank you very much. So far, so good? Okay. So let's go back for a second and go back and look at something we did here. Very first thing I wrote. Does this remind you of anything? Been way back into the first thing we did in first semester. Remember this rule? That would imply they're inverses, right? That's what we've shown there. So f of x and g of x are inverses. That means that whenever we're trying to solve an equation involving a logarithm, we're going to need to use an exponential to cancel it. Or anytime we're solving an equation involving an exponential, we're going to need a logarithm to cancel it. But that also means that the properties of exponents have a corresponding property for logarithms. So you remember how we know like a to the n times a to the m equals a to the n plus m? The logarithmic equivalent of that property is that log base b of rs is equal to log base b of r plus log base b of s. Is that a multiplication inside the logarithm turns into addition outside the logarithm, whereas addition inside the exponential is multiplication outside the exponential. So you see how they're like the reverse kind of property. Same thing true for the quotient. And the power rule is like the exponent of an exponent property. And then the change of base formula isn't something that you'll really use. Now, when I was a student, we used the heck out of this thing because we did not have a calculator that had a logarithm button built into it. What you had to do is you flip to the back of the textbook, and there's like a table that you had to look up the values for like log base 10 or the natural log out of. So if I wanted to do like log base 2 of 3, I'd have to write it as the natural log of 3 over the natural log of 2, flip my book to the back, find my log table, write down the decimal for one, divide by the decimal for the other, and then type the decimals, the division into my calculator. How are you going to do log base 2 of 3? You can type it into your calculator directly with that log base button that I showed you guys. So the change of base formula, while still true, and at times can be useful algebraically, is much less pertinent to your guys' everyday use of logarithms because your calculator can handle log of any base without a problem. Is that okay? So that's one that doesn't get used very often. Now, looking at these three properties, product quotient and power property, we're going to really have two types of problems based on these. You're going to have expanding. So for an expanding problem, you take one log and change it to the sum or difference of many logs. And then there's condensing or compressing. There you take the sum or difference of many logs and change it to one single log. So let's look at some examples of this process and kind of how that works. Well, I guess before we do that, let's do this. For expanding problems, you'd go from quotient to product to power properties, typically. And then for condensing, you go from power to product to quotient, typically. Now, if there's some parentheses in there, it may imply that you have to do one before the other, but that's the typical order. Let's do a couple of examples now. All right. So these are expanding problems. So when we're expanding, the first thing we look for is a quotient property. If I look inside the logarithm, is there any division going on? No, so we don't need to worry about that. Next we look for is the product property. Is there any multiplication going on? Sure is. It happens between the 4 and the x, right? There's one multiplication going on. So using the product property for multiplication, we can do that. Everybody's okay? Now we'd look for power properties. Do you see any power properties going on? Not the way it's currently written, but what about the number 4? What if I thought about that as 2 squared? Now there's a power property was hiding on us. Mr. Kulik, how rude. Well, you know, sometimes that's how it goes. Mathematicians are some sneaky jerks. So that's what the definition of the power property says. The exponent becomes a coefficient. Yep. So that's just the way the rule works. Yep. That's the expanding. So again, we've taken one log and we've broken it up into the most logs we can. What's up? That's okay.
I know you're in the middle. Allison Tyler.
Yep.
Wade Robinson.
He's here. That's okay. Guys, check in at the office when you get here late.
The security guard told me that I wasn't late and just to go to class.
Oh. Okay.
He wanted it.
Well, you can go have words with him
I
later.
will.
Okay. All right. Part B. Again, first thing we do, quotient property. I don't see one in there either, right? Product property? Yes. How many product properties? Well, how many multiplication symbols are there? 2, right? There's one between the 3 and the A and the B. So if we use that product property, oh boy, come on, Kulik. 3A and then B to the 5th. Everybody's good? Now, if I look inside of each of those, do we see any power properties? Where do we see it at? The B to the 5th. So the other ones are just going to stay the same. But that last one will be 5 log B to the... Yeah. They're supposed to be. Again, my pen. I had a battle with OneNote this morning, and I'm still kind of getting over it. It was not being my friend in first hour. We had some choice words to say to one another. You know, I'm still kind of tore up about it. All right. Okay, what do we start with? Quotient property. So if I look inside the logarithm, is there division going on? You betcha. So we have log of the top minus log of the bottom. So far, so good. If I look at each of these logs, do we see any product properties going on? Yeah, which one? The first one, the 2x. So I can break that apart. But there is no multiplication going on in the second one, right? Now we'll look for power properties. None in the 2, none on the x. But there is one in the last one. What is the power property there? What is the exponent? No. It is 1/2, yeah. So you want to think about that as x cubed minus 5, to the 1/2. Everybody's okay there? Now, is there anything else I can do that x cubed minus 5? Is there anything else I can do with that? Is there another power property going on there? It looks like it, but the answer is no. The reason is you have to think about x minus 5 as one thing, or the x cubed minus 5 as one thing. The power on that is to the first. No power property. If it was 5 times x to the third, well then yes, you'd have some more stuff to do. But if it's addition and subtraction, man, no bueno. That's it. That's all we got. This is the end of the road for us. We see the difference between why that cubed is not a power property. It's very confusing at first glance. You expect that to be something, and it's like, ooh, it's not, because it's not going, that power is into the whole insides. All right, what if we want to go the reverse route and condense these bad mama jammas? It's not really any harder. We just have to make sure that we're looking at things in the reverse direction. So when we're doing a condensing, we're going in the reverse order. So the first thing we're looking for are power properties. But instead of looking for a power property with a power inside, we want to be looking at the right-hand side because we're doing the reverse. So we want to look for coefficients out front. So I see two power properties here. Do you guys agree? So that coefficient in front is going to turn to a power inside. So far, so good. Could I, Mr. Kulik, could I have taken the negative sign with the 2? Could I have written that as plus, like log base 5x to the negative 2? Could I have done that? Yeah, that's okay. It is okay to do that. You can think about that subtraction as plus a negative and take the negative sign with you into the exponent. That's okay. I don't typically like to do that, but it's not wrong. Still can get to the right answer. It's still correct. There's nothing wrong with that. Just pointing it out. I wanted to say it once. I don't like doing it that way. I probably won't do it that way, but it's still okay. All right. Next thing I'm going to look for is a product property. So again, since we're going in the reverse direction, we're looking at this side. So we're looking for addition between two logs with the same base. So I see that I do have a product property here. Does everybody feel good there? The last thing I look for is the quotient property. So again, I'm looking for a quotient property that is subtraction between logs with the same base. Now, if I look, I have the subtraction, but the base of my logarithms, not the same. Can I use the quotient property? No, I cannot. That's as good as I can do, what I have written. School, that's rather disappointing. I wanted one logarithm. Well, as long as the bases are all the same, you can get to one logarithm. If the bases are different, you're kind of up a creek. All right, the second one, we had 4 log A minus 3 log AB plus 2 log B. First thing I look for is power property. How many power properties do I see? 3. Now, I've made a mistake in how I've written this. Can anybody see where the mistake is? I've intentionally made a mistake on how I've written that. Can anybody see where the mistake is? I did it because this is a super common mistake that you guys will make. And I want you to look at it and be like, what the heck is wrong with this? And hopefully you remember that, like, oh, that's really, I would do that. That's how I would think to do this. Because this is written how you would think to do it. Isaac.
Is the exponent outside the parentheses?
On the AB?
Yeah.
So it has to do with that term. And it's that 3 needs to apply to both the A and the B. So you need like either a second set of parentheses there, or you could write it like that right from the jump. Either one is okay, but you got to have one of those two. Because the way you've written it is just A to the first times B to the third was the way that I wrote it, which is wrong. We want to make sure we're right. So you got to have that extra set of parentheses in there and make sure that you apply the exponent to the entire product. Good call. Right on. Okay. The next thing I look for is a product property. Do we have one of those going on? Yes. Between which two logarithms? It's not between log AB to the third and log of B squared. It's between log of A to the fourth and log of b squared. Remember, we can add two things in any order we like, correct? If I go back and I look at the product property, the coefficients on the product property have to be 1. That subtraction symbol in front of the other means it's a coefficient of -1. Do you see that? Again, we've trying to choose problems where I'm showing you all the tricks, like all the things that are easy mistakes to make. So we should say this is that okay? The last one then is the quotient property. And if you'd like, you can reduce that fraction, and you end up with just a over b. Does that feel okay? I'm not going to bother with that. All right. All right. So at this point, we now have all the tools we need to do solving. So what I'm going to do here is I have, I don't know, like 6 or so solving examples between exponential and logarithmic equations. We're just going to run through examples on kind of like how to do this. Because in section 15.4, there's no new concept. It's just like, okay, how do we use, exponentials or logarithms to kind of solve these kinds of equations? All right. So remember, when we're solving, we want to use the reverse order of operations, right? Start by undoing any addition and subtraction. The only addition and subtraction I see is locked in the exponent, which means I can't get to it until I've gotten rid of, gotten that stuff out of the exponent. So I'm going to ignore that. The next is multiplication and division. I do see that, right? I see 14 times 1/3. So I'm going to divide both sides by 14. (126) divided by 14 is 9. Now what I'm going to do is I want to cancel that exponent base of 1/3. What cancels an exponent base? Starts with an L. A logarithm. But not just any, I can use any logarithm, but to make this go the easiest way possible, I want to choose the logarithm whose base matches the base of my exponential. So in this problem, I want to use log base 1/3. Those guys cancel out. Then I just add 1 to both sides. And it's calculator time. Now you can do, I want to acknowledge that I could do log of 1/3 or log base 1/3 of 9 by hand. I just don't want to do it. You know what I mean? It is -2. Oh, and then when I add 1, I get -1. Yes, for the whole thing. Yes. Everybody feel good? Not too bad. Let's do another. What's our first step? Okay, do I have any? Okay, what next? Okay, what do I do? Sure do. So 27 divided by 12 is going to be 9/4. Again, you don't have to reduce here. You could leave it as the fraction. It's all going in the calculator anyway. So like, who gives a rip? The calculator will take care of it. But I just second nature, you know. All right. How do I get rid of the exponent base of 3/2? Log base 3/2. And then last step would be to multiply by 5. And then it's going in my calculator. So you get 10. That's correct. Feeling good? So far, so good? All right. Here's a tricky one. This is as hard as they're going to get for your exponentials. Well, be careful because the pieces that are being added are both have variables in them. So you want them on that side anyway, right? So I would just multiply both sides by 4 to start. Oops, that's not times, that's plus. Now, the first thing I'm going to want to do is get rid of this negative exponent. What can I multiply both sides by to get rid of that negative exponent? It's a tricky question here. Remember, when we multiply exponents, they add, right? So I need it to have the same base. And what power do I need for 3? If I add it to negative x, I want something plus negative x equals 0. I want x. Right? So when I distribute it to 3 to the x, I get 3 to the 2x. But actually, I'm going to write this as just 3 to the x squared for now. When I multiply it to here, I get 3 to the 0, which is just 1. And then I get 8 times 3 to the x. What's this starting to look like to you guys? Let's say this. If I just say, what if that 3 to the x is just like a new variable, like y? What kind of an equation does this look like? Should look quadratic, right? So to solve this quadratic, I need it to equal 0. So I'll subtract the negative 8y over. And now I'm going to try to factor this. Well, clearly it doesn't factor. There's not two things that multiply to give me 1 and add to give me negative 8, Mr. Kulik. So we'll use the quadratic formula. So that's going to be 64 minus 4 is 60. And now that can simplify some more, but I don't care right now. Because now we want to put that 3 to the x back. So again, to get the x by itself, now I use.
Good morning, moving prep. Excuse the interruption. At this time, I'd like all seniors to pack up your things and bring everything with you down to the gymnasium. All seniors who pack your things and come down to the gymnasium. Wait, where are we going? Everything with the seniors only.
Bye, guys. Have fun.
We're like going to play with the little kids.
Say hi to my daughter.
Oh, wait, hold up though. Don't go without me. Yeah, God.
Everyone ditch Mary. Quick. Go quick. She should have to walk by herself. It's going to be devastating.
Hi.
That's awesome.
So there's one answer about 1.88. And here's the other answer, which is about negative 1.88. That's the worst case scenario, is where you end up with a quadratic nested inside of your exponential. Let's strike that, reverse it. This is an exponential nested inside of the quadratic, because we had to do the quadratic first before we could get to the exponential. All right, log time. Okay, the same rules, because we're still just solving. What should I do first here? Same rules. What should I do first? Okay. Now, what's going to get rid of log? What is the base on that log? I don't see any base written there. It's 10, because when there's nothing there, we know it's 10. So what exponent base do we need to use? 10. So the 10 becomes a base, an exponent base of both sides. So when I do this, I write the 10s real big. So I can't confuse this as times both sides by 10. This is the exponent base of 10 to both sides. So x is going to be plus or minus 10, right? Now, for all exponential equations, I do. You must check. You have to check your answers, because you can get extraneous solutions for for logarithmic equations. All logarithmic equations we need to check. But I know that regardless of whether I plug 10 in or negative 10 in, it's going to be log of 100, so I'm good. All I'm really checking is to make sure I don't end up with a negative sign inside my logarithm. That's my indicator that it's extraneous. So both of those guys count. They're all good. Let's do another. Ooh, that got real big. Now, if we look at this, this is different than the previous one because we have x's in multiple logarithms, correct? My goal, and when I see this, is I need to condense everything into a single logarithm. So I'm going to start by moving all the logs onto one side. And now I'm going to treat this as a condensing problem. So the first thing I'm going to do are my power properties. And then my product properties. And then my quotient properties. So far, so good. Condensed into a single logarithm. Now it's ostensibly the same problem as before. So what is the base for the logarithm ln? E. So I want to do exponent base e to both sides. And again, I write this like embarrassingly large exponent base e just so I don't confuse myself later when I look back at this. Exponent base e cancels log base e. And e to the 0 is 1. So this leaves me with a rational equation to solve, just like we had last chapter. I think probably the easiest way to do this is to just kind of like cross multiply it. So that gets rid of the fraction. I'm going to, I don't know why I put a squared there. Yep, and I'm going to FOIL this out. I just like a step ahead. So that's minus 5x plus 2. I'm going to subtract the x squared from both sides. Use my quadratic formula on this. It might factor, but since the leading coefficient is not 1, I know it's going to be kind of a pain in the booty to do it. And I'm just not feeling it, you know. So I'm left with 25 minus 16. That's 9. The square root of 9 is 3. So if I add those, 5 plus 3 is 8. Divided by 4 is 2. 5 minus 3 is 2. Divided by 4 is 1/2. But I need to check. So if I go and I say I look at 2, I go back to the very beginning. Oops. 3 times 2 minus 2, positive. 2 minus 1, positive. 2, positive. That answer checks out. We'll keep him. If I look at 1/2, 3 times 1/2 minus 2, negative. I don't care what happens after that. As soon as I see that happen once, I'm going to discard him as extraneous. I'm done. So far, so good. Okay. I feel like this is a good place to stop. We have story problems solving after this, but we're going to stop here for today because 1, the seniors are all gone, and 2, it's enough for today. Because that's going to be a whole boatload of problems to see. And I don't want to go like overboard and end up with like 10,000 problems due. Because guess where we get to? We left off at 36. So we're 36 through 130. Yeah. Yeah.
Mr. Pruitt. Oh.
I know.
I mean, they can't be that long.
They are not that long. No, they are all relatively quick ones. Yeah, I know. Wednesday, the plan would be the homework quiz, and I'm actually gonna scrap the plan of doing 15.4 part 2 and just make it a day to work on your homework set
Wednesday?
on Wednesday after the homework quiz. So we'll do the homework quiz and then just take another hour and try to crank through some of this stuff because there's a whole lot of problems all at once.
Homework was gonna be on the first,
Yep, let me double check on exactly what I wrote that over, but that's absolutely a fair question, one I will absolutely answer. Just give me 1 minute to look it up. And if it's over too much, we might just have it done on a different day or something. We'll see what we want to do here. Hold on a second.
Mr. Cole, can I go to the bathroom?
I sure hope so.
May I go to the bathroom?
Yes.
Thank you.
Yeah, it would be over 15.1 and 15.2, the homework quiz.
so that could get us something.
So 1 through 36. So if you've done that stuff, you should be good to go. Yep, that is all you need. What do you guys say? Fair enough? Fair enough. Again, I try to be, if you assign 100 problems, let's try to find some time in class to work on some of them. So it's not all